I want to thank the previous speaker for taking up some of my time so I don't have to talk as much. Today I'll be talking about advancements in Liutex-based vortex identification. We're going to be talking about the newest core line method and some about objectivity, some objective Liutex. So we're going to be talking about some ISO surfaces and the problems with ISO surfaces, the core line, the idea behind it, some difficulties, the process, and some examples. And we're going to look at the idea of objective Liutex. So we all know Liutex is the rigorous mathematical definition of the pure rigid rotation of a fluid. Liutex provides us with two quantities: Liutex magnitude, which represents the strength of rotation. It is twice the angular velocity, but is also a scalar quantity. The Liutex vector represents the direction of rigid rotation of a fluid. It is also the local rotation axis of a fluid. And it is a vector quantity, which has a lot of benefits. So let's take a look at the ISO surface. A Liutex ISO surface is created by selecting a value of the Liutex magnitude. As you can see on the picture, that is an ISO surface representing one scalar value of the Liutex magnitude. A con of using the Liutex magnitude ISO surface only is that it is not a threshold-free method. The threshold is selected and is arbitrary and can be different for each case. My threshold can be different than yours depending on the case. There is no defined threshold for every single case. My number will not work for your number, and my number is not the number to use. It's also not a vector. We can't use it to show the direction of rotation. So it's just more of just a tool used for general observation, I feel. This is data of, you've probably seen this before already, but this is a flat plate boundary layer, transition layer of, flat plate transition layer of a fluid. So we'll just kind of see some lambda vortices and some hairpin vortices. So here's another example of why not to use, just only Liutex isosurface. Which one of these is the correct vortex structure? It's, we don't know. So we have two different values for the isosurface of Liutex magnitude, yet here we have missing structures that are present in the other threshold. So that is kind of an issue. Which one is the right threshold? So it is to say that Liutex isosurface alone is not enough to represent the unique vortex structure. So we'll move on to a Liutex vector-based method of determining the vortex structure, the Liutex core line. The Liutex core line is the local rotation axis of a vortex. It is unique and therefore can uniquely describe vortical structures. It is threshold-free. That means there's no arbitrary threshold that is needed that changes the location, position, or structure, size of a vortex. It's vector-based, so it can represent the strength and direction of the vortex along the core line simultaneously. We can define the Liutex core line using two simple rules. A Liutex core line is formed by points which satisfy the gradients of the Liutex magnitude cross product with the direction of Liutex equals 0. This simply means that the gradients lines and the Liutex lines are parallel with each other. And this is only true when you're very, 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 very close to the core line. And obviously, Liutex exists. So Liutex magnitude is greater than 0. R is greater than 0. And that's just what I said. These may be two simple rules, but in other words, we can also say that we can define the Liutex core line to be the local maxima of the Liutex magnitude within the plane normal to the Liutex vector. So if I'm pointing this way in my Liutex vector, it should be the max, the magnitude of the starting of the vector should be max within the plane, the local plane, the local region. It should be a local max. So there are some difficulties when finding the Liutex core line. Although the criteria for finding a Liutex core line point is defined, finding the Liutex core line is a different story. The reason why points on the Liutex core line are so difficult to find is due to computational ability. Well, because there doesn't really exist an infinitely discrete mesh or grid for any simulation. Liutex core line points lie on the local maxima. The problem is that data grid points do not generally align with the local maxima. We could see this figure, which you probably saw earlier in Dr. Yu's presentation, where the green is the ISO surface of the vortex, and then those points are the grid points. So those are my nodes. And you can see that the core line, which is that black line that goes through the center of that structure, doesn't intersect or even touch like some of the points. And those are the points that we check when we're going through the data. We go, that node, does this satisfy? That node, does this satisfy? Well, that node is so close to it, but it's not exactly, so it does not satisfy, so it gets excluded. So there's other things that we have to check to make sure that we get at least some points, because I don't want to say it's impossible, but it's very, very hard to find the exact center, right? We don't have an infinitely continuous, smooth function that we could just derive. We have discrete data. So this is the process. This is a little more technical, but not too technical. It can be weird because it's new, but this is the method, the first part of the method for finding the Liutex core line. And it's using a predictor corrector method. So we're basically going to one point, checking it, checking around that point, and then comparing it, and then moving if necessary. So we're going through the nodes, the interior nodes, and we're checking if modified omega Liutex is greater than 0.5. Now, this might seem strange, but modified omega Liutex we have found to be a very reliable method to describe the structure of a vortex using an ISO surface. Mostly because it's threshold free, and we can depend on having a good representation of the structure. So if it's greater than 0.5, we know for sure that we're getting closer to the, we have a good volume to go into. So we're at a node, and it's greater than 0.5. And then so now we step into the Liutex vector direction. So we look at the Liutex vector direction, R, and we move in that direction a distance of d. D is dependent on your grid. So your grid may be this course. Well, this point and this point, and this point, and this point are around the core line. But they're not touching or intersecting the core line. So what this method does is we look at this point, and we look up, left, down, right, and we generate these points. And notice that this distance that we traveled is shorter than our grid, like resolution. That way we can get in between the volume or the space and find exactly where we're going. So this is your distance D. Right. So we're stepping in the direction of Liutex, a distance of D, which is reliant on our grid size. Now that we have these locations, we will calculate Liutex. We will calculate Liutex, both the magnitude and the vector, because we will move to a point. We will move to a point if the magnitude is larger. Hello? It's probably dying. Hello? All right, so I'm going to go through this a little quicker. You are more than welcome to talk to me or Yiffy about this afterwards. But it's almost coffee time. What's up? Oh yeah. So we interpolate to find the new values so we can take another step if we need to. That's basically step 3 and 4. And then 5, we calculate the Liutex magnitude. Number 6, we select the point with the largest Liutex magnitude value, switch to that point, and then we return to step 2, in which we generate that little small local grid and check the nearby points again until we satisfy the conditions of the core line. If the point satisfies the conditions of the core line, we add that point to our list of core line points. And here's another kind of diagram of step 4, which is where we kind of search for around the node and the point that we step into, that we node and we step into, to search for the local max Liutex magnitude value. So we will check at each of these bottom, right, top, left points and see which one's the higher value. And then if it is, we move there and check again. After you've collected all of your points, you have a whole lot of points. We need to group these points. At this point, you can, at this point, you have all the Liutex core line points. The issue is you may have too much. Some need to be filtered. You have a lot of noise. So you group the points to where each group is its own Vortex core line. So to do that, we start with one of the Liutex core line points. We check if any point is near it by a specific distance, and that is also in the direction of the Liutex vector. So if that point exists, then we add that point to our current core line point list. If we are at a point and no other point satisfies the list, then we start a new core line list. Continue to do this until you're done. Then step 3, we got to filter. So when you're building these little lists of core lines and vortices, you're going to have a list of 1 point, a list of 2 points, a list of 3 points. That's not really enough to justify it being a core line, if you think about it, depending on how fine your mesh is. We can see here that, here. So an example, is this touch screen? No. Is it? It is. Oh. Okay, on step 3, the bullet says if the core line list is 4 points or less, it may be different depending on how many core lines you would like to see and how short you would like to see, then throw that whole list away. So throw away the list with 1 point. throw away the list with 2 points, throw away the list with 3 points. They're too short, they're just little stragglers, and they need to be filtered out. Once you've found the Liutex core points, you can plot them with your grid, within your grid, and visualize them as Liutex core lines. And here is a figure where we have a transparent isosurface where you can see the core lines going through the center of the isosurfaces, and they are colored and contoured with the Liutex magnitude, which you can see describes the strength of rotation at that place in the core line. We can contour the points with Liutex magnitude to see the rotation strength. And if we want to see the rotation direction, we could also plot the Liutex vectors at each point. Now, I don't have any of these plotted with the Liutex vector, because these aren't, I borrowed these figures. But yes, you can add the Liutex vector to each one of the points, and you can see the direction of rotation for each, for anywhere in the core line. Here is another figure by Yafei. And here at the very top, we can see the clear core line structure. The middle, we just see an isosurface. So this is just an arbitrary isosurface. All isosurfaces are arbitrary. But this one looks decent. As you can see, we're missing a lot of the structure at the tail end here. But the core lines catch it. They also catch the stronger vortex structures, like some of the necks on these, I don't know what these are called, the hairpin vortices, these little legs, little necks. Some really strong ones and very weak ones. And you can see the colors describe how strong it is. And if we look at the bottom, we can see that these features even extend beyond the point of the isosurface. So we get more of a description of the vortex using these core lines than if we just use an isosurface. This is a side view of the same thing. You can kind of see this little cool spot right here. Kind of illustrates the core line. Here are another images of the core line. You can see that these little blips here, these are the short core line points that I was talking about, where they're just 1 or 2 or 3 points long. So you can kind of see how they're just kind of making it a little messy. So you can remove these and have only the long ones. And if we look at this picture, you can see that those short ones have been removed, and we can see just the longer, more defined core lines. Oh, this is a video. You can see the core lines forming, especially here. You can see in this area how these are formed. These become this. And we can see the structure change, the unique structure change. Okay, I don't have time. That was the Liutex core line. I'm going to be talking about objective Liutex now. We have found that Liutex itself is Galilean invariant. Liutex is also the same in different inertial frames, inertial reference frames. If we can find Liutex in one inertial reference frame from data collected from inside a non-inertial reference frame, then we can say that the vortex structure generated by Liutex is objective. This is the concept of objective Liutex. We suppose the angular velocity of the observer is capital VA. And for the velocity in the inertial frame and the velocity in the non-inertial frame, we have this relationship where we have the transformation T, transformation matrix T here, going from little ijk to big ijk, I think. That's big ijk, yeah. And we're gonna make an assumption and let our origin and basis, or like our axes, be the same in our inertial frame and non-inertial frame. That allows T to be equal to the identity matrix. So we have, so we now got rid of the T, and we just have the velocity gradient in the non-inertial reference frame. All right. So the point is, okay, that's right here. We need to find the inertial data from the observer's non-inertial reference frame. So we need to find the angular velocity to solve this equation. We can use vorticity to help find the angular velocity, where vorticity is 0 in the inertial reference frame. And since our inertial and non-inertial reference frames share the same origin and basis vectors, I probably should have deleted the same coordinate system. This makes our velocity, angular velocity, equal to negative 1/2 vorticity. But this is not just any vorticity. This vorticity is the most common vorticity in your data. So, most common vorticity vector in the non-inertial reference frame. So the frame that you're observing from. So here we have inertial Liutex isosurface. So this is just the regular Liutex isosurface. On the right, we are in the non-inertial reference frame, observing with angular velocity of 0.1, 0.2, 0.3, and this is what it would look like. The goal is to be observing from a non-inertial reference frame, this frame, and go back to this inertial reference frame, and that's what we're doing. And to do that, we find the most common vorticity vector. Once we do that, we can find the angular velocity, plug it into this equation, and what we get is, this is our original Liutex data, and this is the calculated inertial reference frame data. And you can see they're very, very similar to each other. And this table is the vorticity vector we found. These are vorticity vectors we found, and this is their presence in the data. So there's 63.4% of vorticity values is this vector. So we're using that. We're using the velocity is negative 1/2 of that, which is this. And that's what I have so far. It's time. Okay.